All right, day 9. About to start. What's going on? We have just a list of numbers, and we're supposed to do something. Uh, ah, how long is this? 20,000 characters. Okay, so what is this? ID number. End of the desk to the leftmost. Okay, think. Not big. Okay. Position of the file ID. Uh, yeah. 5072. It's wrong. 009981118882777 2450 is still wrong. Hmm. Bunch of sixes. Not so many sixes. What happened to all the sixes? They got moved. One, 928. Of course. All right. 0, 0. It's still long. Uh, 5, 8. Wow. Okay. Some points could have been faster. I'm not quite sure what went wrong. I guess it took me a little while to. I don't know. I feel like I was just kind of slow implementing. Anyway, what's going on here? So we're given this sequence of integers, and that maps to a sequence of files on disk, where each integer corresponds to either a file or free space, and then we want to do some kind of compaction algorithm. Um, so in part one, that's just like each individual character, you move it left. Um, and in, so, whatever, this 9 moves to here, this 9 moves to here, this 8 moves to here, this 8 moves to here, and so on. Right? You just like fill it in, and then you compute a score, which is just position times number, 0 times 0, 1 times 0, 2 times 9, and so on. Um, and okay, so this is like the implementation for part 2. Let me see if I can clean it up for part 1 as well. I think. So I guess I should explain. In part 2, we are not going to move individual characters. We're going to move entire files. So like we move this 9 to here, but then the 8 can't fit here, so we don't move it there. We actually it can't fit anywhere apparently, so we just leave it alone. But like the 7 can fit in this block of size 3, so we move it there. And the 6 can't move, the 5 can't move, but the 4 can move to here. So okay, we get less compaction. Um, so I'm thinking that in part 2 we treat each file as a block, and in part 1 we treat each individual character as like a file. Um, so hopefully that will work. I guess we will see. Oh yeah, also I had that bug. Wasn't ideal. Now apparently I have more bugs. Oh, I see. It doesn't even think that this is a valid spot. Seems weird. Oh, okay, this is wrong. Forgot how pause worked. Cool. So that prints 1928, which is the right answer for the example, and 2858, which is the right example for part 2 of the example. And interesting. This is actually very slow on part 2. Okay, it does eventually print out something, so whatever, we'll just take that. 626289, something or other 328, that looks right, and 628, something or other 845, that looks right. Okay, cool. So this code now solves both parts. So let me explain what I'm doing. So first I read the input, and then to solve the input, I first like expand it out into what's currently in the file system, let's say, and where the files are, and where the empty spaces are. And this is an index. Yeah, sure. No, this is an index into final, and this is I see just the current file ID, which they said just increments by 1 every time. Okay, so uh, we go through the input string, and if we're in an even position, that means we should make a new file. So in part 2, we mark down a whole new file. And then either way, we fill in like the current contents of the file system, whether you have this file. And if we're in part 1, then we say, and this is something that we could move with each individual spot. Then we increment, um, where we are in the file system. And at the end of this, we increment the file ID. So the next time we go through this, first we place it on the file 0, then we place it on the file 1, etc. Otherwise, we're making an empty space. So in part 2, we say, okay, we record that we have some space at this length. We fill in empty space into the file system. And in part 1, we say, okay, here's a position where you could put a single character. Actually, I think strictly speaking, this is not necessary. The way that I wrote this will handle... Yes, we'll handle that correctly. Okay, so maybe that says... That's kind of nice, because then now I only have like one place where I'm looking at part 2, which is just whether or not you can move a whole file, or only move a whole file. You can also move individual pieces of the file. And then we go through each of the files that we might want to consider moving from right to left. That's what they say to do, is from right to left. And we go through all the space where we might be able to put them, this time from left to right. And if we're actually moving it to the left, and we have enough space, then we can move it. So we wanted to move a file of this size. So, check that it was where we thought it was, delete it from where it was, and put it in the new space. And then mark down that we've like used some of this space. So the new, like we've used the first size, bytes, I guess, of the space. So the new start is over by size, and the new size is minus size. And this might be 0, in which case we shouldn't use this anymore. And I guess, whatever. We could delete this from being considered again, so we don't waste time trying to put things of size 0, but then I need to mess with this list as I'm iterating over it, and it's just easier not to do that. So this is the, like, I don't know, heart of the problem, is doing this movement. And then we can just compute this checksum. So, and it says basically for all the spaces that are non-empty, yeah, if it contains free space, skip it. So if they're non-empty, then you multiply the index times the thing there, and that's just the answer. So as I said, the only difference between part 1 and 2 is that in part 2 we consider like moving whole files, and in part 1 we consider moving each individual byte of the file. And so this solves both parts. It's a little slow in part 1. I don't, it's just like more files to move, but it only takes 2 seconds, so whatever. Yeah, so that's it for today. See you tomorrow.